My name is Norbert. I'm with the Fraunhofer Institute in Jena. We have quite some experience in micro-optical systems, so I run a group there that is dedicated to the design of micro-optical systems. I just show a couple of examples that are more or less based on double-sided replicated microlens arrays. So on the right-hand side you see an integrated spectrometer solution giving you 33 spectra at once in the visible range, combining metasurface gratings and refractive optics. On the second from the right you see miniaturized microscopy solution proven in wide field as well as fluorescence imaging, giving you 160 micro objectives with 10x magnification and 0.3 NA. We do multimodal imaging using tile filter approaches and combining it with micro objective arrays. But today I want to solely focus onto the application shown on the left-hand side on illumination and pattern shaping using microlens arrays by means of maskless approaches. I don't think I have to introduce this light carpet approach to you. It has been shown many times today. It was invented more than 10 years ago in Jena. What you basically do is you use a fly-side condenser. So these are two spherical microlens arrays separated by their focal width. And if you introduce an array of microslides under the left side of the array, so under the condenser lens, then the projection lens images this spatial distribution to infinity. That's the approach. It has been adapted by in these lucid air approaches and Hyundai Genesis approaches, going to two wafer setups. But nonetheless, if you want to go to headlamps, you need to discuss high brightness applications. We need to discuss price issues. We are introducing a pattern mask by means of any lithography step might be too expensive. And of course, as soon as you introduce losses, then you introduce heat dissipation, which potentially might lead to accelerated aging. So what can be done to get rid of this absorption? As I told you, the projection lenslet array just projects the microslides to infinity. And if we get rid of the microslides, what can we do? We can play with the apertures of the condenser lens array. So on the left-hand side, you see that the apertures of the entrance lenses are varied in size. And by varying the size of the entrance lenslets gives you the option to project different widths of the pattern. This is shown in the middle at the bottom of the slide. Additionally, you can shift the vertices of the projection lenses, so you introduce a tilt there optically. That means you can generate asymmetric patterns. In conclusion, replacing the microslides by irregular lenslet arrays gives you a versatile tool for generating almost arbitrary patterns, and you can reach 100% efficiency provided that you manage to find solution to have a 100% fill factor for the entrance lenslet array. Just as an example, think about you want to create this sort of Swiss cross intensity distribution. You want to project it into infinity. If you do the light carpet approach, shown here as a 3x3 array, then you have to introduce masks, and these masks will simply take away approximately 50% of your illumination intensity. If you manage to prepare condenser lenslets that are spherical lenses with a Swiss cross shape of the base plate, then you can create a space-fitting arrangement of these condenser lenslets, and you can create a pattern shaper with 100% efficiency. Okay, so in the rest of the talk I want to introduce two applications of this approach to you. I guess I don't need to explain the application anymore. We have seen it many times already. The idea is to mount a projector inside the outer mirror of the car, so the height of the projector will be roughly 70 centimeters. Target was to have a semi-dynamic daylight visible ground projection of a blinker solution. We have heard about étendue issues today, so getting bright means that the projector gets large, that the projection aperture gets large. That's why we decided to project all three chevrons with one projecting element, and this can be done by exploiting something that we usually want to avoid, and that's this crosstalk. So we utilize light, leaving one channel and being projected by a neighboring channel. So in detail, we have 3 LEDs that are switched individually. The center LED illuminates the shape of the reticularly. We create a space-filling array of these chevron entrance lenslets, and if you illuminate it perpendicularly, then the central lenslet is imaged by the center projection lens. And if we add 2 additional lenses, illuminating the system in plus and minus second order crosstalk allows us to project 3 chevrons to be switched individually. Here's the example. On the left-hand side, you see microscopic images of projection lenslet arrays. You see this chevron shape and the condenser lenslet array on top and the projection lenslet array at the bottom. You see the simulated distribution on the road, as well as photographs in a dark lab in the middle, and on a cloudy day at lunchtime in Jena at the street. With this system, we reach a brightness in the range of 7 kilolux for the smallest chevron. That means this is the chevron that is closest to the projector. I have to admit, maybe you can see it or not, that there are slight stray light issues almost already visible in the dark lab, and these are due to Z-height jumps of the projection lenslet array, which will be avoided in future designs. Just a few words how to prepare these lenslets. We use grayscale lithography developed in Jena to prepare master structures and then replicate these master structures by means of polygon glass replication using Swiss mask aligners for achieving double-sided aligned pattern shaping modules. How about creating not such symmetric distributions? So you all know this headlamp or low beam distribution, where the target is to generate a very sharp cut-off line with this kink shape in the middle and requiring roughly 30 kilocandela in the high intensity region of the beam. How to do this? Again, we use double-sided micro-lens array. So we have an entrance lenslet and a projection lenslet, and if we want to create this kink in the distribution and this short cutoff line, then we have to modify the shape of the base of these entrance lenslets. So if we introduce this kink-shaped structure there, then it will be imaged into infinity or in a certain projection distance, but going towards space-filling arrangements of microlenses then will yield kinks on both sides of the pattern. And that's originally not intended, because the target solution is a smooth distribution of light towards the ground. So what can be done? And there are 2 approaches applied. The first one is we play with the height of the condenser lenses. Playing with the height of the lenses shifts the kink at the bottom side in vertical direction and smoothens the pattern. And second, we can also play with the lateral alignment of these kink structures, and doing so smoothens the beam in the horizontal direction. And combining both approaches gives you this result. On the left-hand side again, you see the condenser lenslet array, you see the kink-shaped structures, You see condenser lenses with different heights to do this vertical smoothing of the beam, and on the right hand side the projection lens array is shown with an aperture size in a range of 250 to 300 microns squared. At the right hand side you see one hand holding a single module for projecting this low beam distribution. The aperture here is 20 by 35 millimeters squared, and this is solely one LED being shaped. So looking at the pattern that we reach, you see that there's a very sharp cut-off line with a clear kink structure. You don't see any color effects. This is a color photograph. And with this single module, we reach approximately 7 kilocandela in the high intensity region. This is an LED with 385 lumens output, so this is from the lowest bin at that time. If you use improved binning, then you can have almost 600 lumens output, and this would take this intensity to more than 10 kilocandelas. So from our point of view, the full low beam function at a car could be delivered by 4 modules. It's worth to say that the total transmission of the system is at the range of 75%. There's still a minor issue, but still below the ECE regulations with stray light, as you see at the bottom left, in the logarithmic scale. Again, the stray light is due to height jumps in the condenser lens array, and this is tackled in future designs. Yeah, that's it. That's already the conclusion of my talk. I have introduced maskless irregular condensers for pattern shaping to you. From our point of view, the advantage of the system is that you don't need a lithographically shaped microslide pattern anymore, and this gives you the opportunity to prepare monolithic pattern shapers that can be produced by embossing, molding, any technologies. We show one example here from a previous project where such a blinker structure had been prepared by injection molding. This requires double-sided arrays that are aligned with respect to each other, and once this technology is available, the way is open towards large area pattern shaping, potentially using curved elements and so on. I have shown 2 initial examples from previous project, the low beam and the blinker application. There's an ongoing design on these topics, mostly dealing with improving stray light issues by handling sec height jumps to ease replication to direct the scattered light into high brightness regions of the distribution. But still, these are 2 modules which have almost identical micro-optical channels. So we are aware that there are other approaches combining a headlamp distribution by superimposing 2 or more different patterns. This could be applied here as well. Furthermore, one can think about combined functionalities to develop mask-free 3D light field luminaires. One could combine low beam projection with diffuse emission in daytime running lights and so on. So there are many ideas. So, of course, I want to thank all the colleagues who did this nice work, most importantly Peter Schreiber and his colleagues, as well as the colleagues from our microtechnology, and I want to thank you for your kind attention.